Hello, my name is Gerhard Adam, and in this set of modules we will continue exploring the mainframe environment. In this module we will introduce the z/OS operating system by examining the four main areas of control. We will look at memory management, task management, I/O management, and resource management. Since this is an overview, it is important to remember that these topics will not be explored as deeply as necessary to resolve all of the questions that may arise. So you should use this material to develop an overall sense of the z/OS environment rather than focusing on specific technical details. Memory management can be quite complex because it involves managing the physical resources of RAM memory, but also because it is used by the operating system and programs to perform work. As a result, there are concepts that will be explored in the next few slides so that we can make sense of how memory is used in a system. One of the first points is recognizing the difference in what we mean when we talk about virtual storage versus real storage. Even here, there is a distinction between the benefit of virtual storage from an operating system's perspective versus the usage it provides for programs. Another concept that we need to examine is how different areas of memory are assigned for specific uses. This occurs so that we can more readily separate out those areas that are used by programs from those that are used and required by the operating system. By separating these areas, we can also provide protective actions that prevent a program error from ever overwriting memory that might be in use by the operating system and cause a total systems failure. Finally, we will also discuss the concept of paging, where the storage can be identified as being active or inactive, and when we have a higher demand for memory of running work, we can move assigned memory that is idle to external disk storage in an operation known as paging. Let's begin with the concept of a memory address. Since programs and the data they are working on all reside in RAM memory, then we must have a way of being able to locate these items. If we have 4 gigabytes of memory, then we have 4 billion bytes of data that may be in memory, so having some means of locating information is fundamental. The way this is done is that each byte is simply numbered, beginning from 0 to whatever the highest byte count is for the memory installed. Therefore, if we have 4 gigabytes of memory, then the addresses that can be referenced would go from 0 to a little more than 4 billion. This number is referred to as an address. So in order to find things, then the item we are looking for must have an address. In this way, between the operating system and programs, addresses are maintained or saved so that we can always get what we are working on. If we happen to use a wrong address, then the program will likely terminate with an error. Now that we have an address, the operating system assigns a range of addresses to particular functions within the operating system. In this way, we can reserve memory for operating system use, and then whatever hasn't been assigned would be available for programs that are running. Again, this division into areas is a design decision used by the operating system to allow better controls for determining what areas can be accessed and changed by programs versus those that are owned by the operating system and cannot be modified by running programs. Since we've just seen how addresses are used, we also have to consider how the system can track these numbers. Over the years, there have been several different implementations as computer architecture has evolved. In the case of z/OS, the early systems were all based on 24-bit addresses. Since a bit is simply a 0 or a 1, then in binary the maximum value that can be stored in 24 bits is 16,777,215. As a result, this also represents the maximum amount of memory that can be installed on such a system. Similarly, when the architecture was revised to 31-bit, then this allowed up to 2 gigabytes of memory, and now the current implementation of 64 bits allows up to 16 exabytes of memory. As a practical matter, there is no technology to actually allow that much RAM to be installed, but the architecture is positioned to allow it to grow. With these three address modes, z/OS is referred to as a trimodal system, meaning that any program can run in any of these three modes, including switching between modes while it is running. This allows extremely old programs, which may have originally been written on 24-bit systems, to continue to run on modern 64-bit systems without modification. It also ensures that programs with different modes can communicate with each other because of this ability to dynamically change the mode that is currently active. In this screen capture, we are using a z/OS performance monitoring tool to explicitly look at what is in system's memory. The column on the left indicates the address of the memory location we have chosen in hexadecimal. The 4 columns in the middle of the display represent the data that is actually stored there. The display on the right is merely there to provide a translation of the hexadecimal information in the middle 4 columns, so that if there is data which can be easily read, a programmer can quickly see what is there without having to work out what the hexadecimal values mean.